In this video, we're going to talk about kind of one of the largest and most complicated things dealing with limits, which is limits involving infinity, and then also limits involving zero. This one can get a little bit conceptually weird and a little bit strange, but at the end of the day, once you kind of get the hang of it, they're not terribly difficult questions to get the answer to. But before we get into the calculus, we have a little bit of a pre-calc question, right? Just dealing with some infinity in general. Here it gives us a sample rational function, which I already have graphed for us. I just set the top equal to 0 to find the x-intercept, and then you just plug in 0 to get the y-intercept. That helped me get the graph. And there we go. If you want to read the rest of the stuff, you can always just pause the video and then read all these things. But generally what we're doing is we're checking limits that somehow involve an infinity. So that means they either go to infinity, so the right and the left side, we call that the end behavior, which you should have seen in pre-calc, but then also a limit around a vertical asymptote that may either go up to infinity or down to negative infinity, right? So we're going to kind of be looking around the asymptotes today and then writing the limits corresponding to them. So again, you can pause it and you can read everything. I'm not going to read it to you because that's just going to waste time and make the video longer. I'm just going to jump down straight to here. For our example, describe the two limits around the vertical asymptote and then describe whether or not an infinite limit exists. Okay, so let's go for it. We've got to do limit from the left, then we'll do the limit from the right, then we'll see if that overall limit is going to exist. So here let's do the limit from the left. So we'll take the limit. Remember, my vertical asymptote is at 4, so we'll take the limit as x approaches 4, but only from the left side. And then we'll do the limit from the right. So it'll be the limit as x approaches 4, but from the positive side. So we're going to see if those two things exist, and if they do they match? Because if they don't, then the overall limit will not exist. So here's my vertical asymptote. It's at 4. If I start on the left side of this graph, and then I come back towards my asymptote, it looks like that limit from the left is going to take you down towards negative infinity. Whereas if I approach my issue from the right, if I start on the right side, then I come back towards my issue, it looks like that right-sided limit is going to go up towards a positive infinity. So we have the left side that goes down, we have the right side that goes up. So I could say, therefore, remember the little 3 dots is the mathematical symbol for the word therefore. Therefore, this overall limit, as x is going to approach 4, does not exist because your limit from the left doesn't equal your limit from the right. It's possible, like if this asymptote was squared, then both sides would go up, and then possibly that original limit would exist, and it would be either a positive or a negative infinity if both sides went down. But generally, when the asymptote has an odd multiplicity, one of the sides is going to go up, the other side is going to go down, so overall, you're going to have a problem with it existing. And then I also want to kind of be concerned with the two one-sided limits, like on the right side of the graph and then on the left side of the graph, right? The end behavior. So the right-sided end behavior is going to be what happens as x gets very large, right? As x goes towards infinity, as that graph moves to the right side of the graph. And then your left-sided end behavior is as x goes towards negative infinity. So these aren't limits that result in an infinity. These are limits as x goes towards infinity. And then you have a limit as x goes towards negative infinity, right? So this would be the right-sided end behavior, and then this would be the left-sided end behavior. Kind of ran into the hole there, sorry. So let's look around this right-sided end behavior, right? Infinity would be really, really, really far down the right side of this number line. So we're just going to hop on this function, and then we're just going to go as far to the right as we can. And then we know, right, as this graph goes to the right, it's going to end up getting closer and closer and closer to the horizontal asymptote. So as you start on this function, and then as your x goes towards infinity, as that graph moves farther and farther to the right, those y values are going to be approaching 2. And then your left-sided end behavior, as x goes towards negative infinity, again, here's your horizontal asymptote. Just start on your function. Then as your graph moves to the left, as your x values approach negative infinity, the y values are also going to be getting closer and closer and closer to 2, because that's your horizontal asymptote. So for a rational function, if you have a horizontal asymptote, like that is going to be the right and the left-sided in behavior. So you could say this overall limit, well, I guess you really wouldn't say an overall limit, because you're not looking at like, hey, 4 and then the left side of 4 and the right side of 4. Like these are just two separate limits. The right side of the graph is going to approach 2. The left side of the graph is going to approach 2. For any rational function, the end behaviors should be the same, right? Because you're only going to have one horizontal asymptote. It's possible that later on you'll see functions that have different end behaviors on either side, but just kind of keep it in the back of your brain. The right-ended behavior is as x goes towards infinity, right? The right side of the number line, and then your left-sided end behavior is as x goes towards negative infinity. So these limits involving infinity, they could be limits like around some other number that end up going to infinity or negative infinity, or it could be a limit as x goes to infinity or negative infinity, right? So a couple of different things that we could be dealing with. All right, so the next stuff is a little bit weirder. Let's think about just some basic number sense, right? So here I've got a list of numbers written out, and this is going to be a little bit strange, but hopefully it makes sense. We got 1, 1/2, 1/3, 1/5, 1/10, 1/100th, 1,000th, right? And it looks like in that list the denominators are getting larger, right? It's 2, 3, 5, 10, so on and so forth. So let's see if we can get the pattern. If you need to, you could go to your calculator and you could type all these things in and you could get the decimal representations for them. I kind of hope you don't need to, but you could if that helps you see it. But in general, right, as this list moves to the right, as the denominator gets larger, the fraction overall is going to get smaller, right? Assuming the numerator stays the same, if the denominator gets big, then the fraction overall gets small. It's like if you have 1 pie, if you're going to split it between 2 people, you're each going to get half the pie. But if you have to split it between 20 people, each person ends up getting a much smaller piece, right? So the bigger number that you divide it by, the larger the denominator is, the smaller overall the result is going to be, right? So if the denominator gets big, the fraction as a whole gets small. And then here's the kind of extension piece that's going to help us deal with these limits. Now, if this denominator gets really, really, really big, so if you end up having this denominator, so you have some number in the top, and if in a limit question, if that denominator ends up approaching infinity, remember, if the denominator gets big, the fraction overall gets small. Here, if the denominator gets closer and closer and closer to infinity, right? If the denominator gets really big, then this fraction as a whole is going to end up getting really, 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 really small, and it's going to approach 0, right? So if the denominator approaches infinity, then the fraction overall is going to approach a value of 0. It's kind of just an extension of this same idea. If the denominator gets big, the fraction overall gets small. So if the denominator gets infinitely big, then the fraction overall gets infinitely small, and it's going to get closer and closer and closer to 0, the larger that denominator gets. Right, now let's think about the reverse case. Here I have another list of numbers. I have 1 100th, 1 50th, 1 20th, 1 10th, 1 5th, 1/2, so on and so forth. So here I actually started with a fairly big denominator, and then the denominator gets smaller each successive term, right? So this is kind of the reverse direction. If the denominator, again, you could change these into the decimals if it helps you see, like, and compare the two numbers and see which one's bigger. But here, right, that's a pretty small decimal. This one's a bigger decimal. That's a bigger decimal. So here we can see that if the denominators get smaller, then the fraction overall is going to get larger. Right? If you split something between fewer people, then every person ends up getting a bigger piece. So if the denominator gets big, the fraction overall gets small. So if it gets infinitely big on the bottom, the fraction overall will get infinitely small and approach 0. And then you have the reverse case. if the fractions overall, or sorry, if the denominator gets small, the fraction overall is going to get big. So here's the weird thing for you. If you have a number on the top, and this is only going to work if you're working within a limit, but if you have some number on the top and you end up approaching 0 on the bottom, right? If this denominator gets really, really, really small and it approaches 0, then this fraction overall is going to end up approaching infinity. Now, it could be a positive infinity or a negative infinity just based on the ratio of these two. Like if that's a positive number and you're getting closer to 0, but you're on the positive side, right? If this is a positive ratio, then you would have a positive infinity. But if this number in the top was a negative, then of course overall you would go to a negative infinity. But conceptually, if the denominator gets small, the fraction overall gets big. So if the denominator gets really, 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 really small, approaches 0, the fraction overall is going to get really, really, really big and is going to approach a value of infinity. And then you just worry about the plus or minus kind of at the very end. Now remember, in math, you should never actually divide by 0. But here, we are not dividing by 0. You can only do this type of a thing when you're working with a limit. And when you're working with a limit, remember, we're not actually plugging in that number. We're just trying to see what happens as I get really, really, really close to that number. So it's strange. Mathematically, we're plugging it in, but conceptually, we're actually just getting really, 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 really close to it, and we're trying to see the behavior and the trend as to what happens when you get really close to it. So if you're just working through an equation and you're just plugging in numbers and you're just trying to solve, then yes, for sure, you should not divide by 0. It's only within the confines of a limit question where it is going to be acceptable to end up having a 0 in the denominator, right? So let's recap. If the denominator gets big, the fraction gets small. So if the denominator gets infinitely big, fraction overall gets infinitely small. And then vice versa. If the denominator gets small, fraction overall gets big. So if the denominator gets infinitely small, approaches 0, then the fraction as a whole is going to get really, 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 really big, and it's going to approach either a positive or negative infinity value. Let's fill in these things at the end, right? Some little statements for us. Okay, if I have some resulting limit and I get some number over a number, well, that's fine, right? That answer is just a number. And you could leave it as 3/7. Like, you don't have to convert it to a decimal. Like, the fraction's better. But anytime you get a number on the top and on the bottom, that's great. That's a really easy, nice answer. If you have a 0 on the top and then a number on the bottom, that's also really nice. The answer is 0, right? 0 divided by anything is just 0. If you have an infinity on the top and then a number on the bottom, like infinity divided by 2, well, that's still infinity. And then if you have a negative in one of those two layers, right, either in the numerator or in the denominator, the result could also potentially be negative, right? So just kind of watch out for the negatives if you need it. But in general, if you have an infinity divided by a number, the result would still be infinity. And then here, if you have a denominator that gets really small, the fraction overall is going to get really big. Remember, you would watch out for the plus or minus, but here I'm just kind of assuming that everything's plus. And then for this last one, if you have a number on the top, and if the denominator gets really big, the fraction overall gets really small. So limit questions are going to be really nice as long as one of the layers, either the numerator or the denominator, as long as one of those two layers is a number, you're going to get an answer, right? If both of them are numbers, super easy. If the bottom is a number, super easy. If the top is a number, it's a little bit weird conceptually, but you're also going to get an answer pretty quickly. The weird things are whenever you get zeros, the lack of a number, when you get zeros on both the top and the bottom, or when you get an infinity on the top and on the bottom. Remember, those are called indeterminate forms. We're going to work a lot more with this later on in the year. We're going to do something called L'Hopital's rule, but for now we just need to know that if I have a 0 over 0, like that doesn't reduce to 1 or that doesn't reduce to 0. 0 over 0 is indeterminate. We cannot determine what that answer is going to be by just plugging it in. We have to do some type of a strategy in order to get the answer. And the same thing's going to be true for this infinity over infinity. That had better not reduce to 1 on any of y'all's papers or quizzes or tests this year. right? Infinity over infinity is not 1. Infinity over infinity is an indeterminate form, so we cannot determine what that answer is right away by simply plugging in. We have to do something. Remember, we started to learn the strategies for how to deal with these. We could factor and reduce, we could combine and simplify fractions, we could use the conjugate, we had those 2 special trig limits. Really today we're going to focus on this, and then we're going to touch back also on the 0 over 0 just a little bit. Right, so a little bit strange. Hopefully this makes sense. If the denominator gets big, fraction overall gets small. If the denominator gets small, fraction overall gets big. Okay, let us start doing some of the examples on the next page. Okay, again, you should probably read these 3 ways to evaluate a limit. That gives you the infinity over infinity, right? Whenever you have a limit that's going towards infinity, or negative infinity, that doesn't really matter, right? It could be plus or it could be negative. You're going to have 3 potential ways to get these answers. This is dealing with the end behavior, right? The positive infinity is the right side of the graph, the right-sided end behavior. The negative infinity would be the left-sided end behavior. So whenever we're trying to figure out what the graph is doing on the far right side or on the far left side, we have 3 strategies. I'm going to show you the longer way once, and then I'm going to work most of the questions the shorter way, and then we can kind of just check our answers by doing this very quickest way, the shortest way, which is just using your horizontal asymptote rules. I would really suggest that you do everything this middle way, right? It's kind of Goldilocks. That one's too long, that one's too short. You just don't show enough work to really get full credit. This is kind of just right in the middle. So I'm going to show you all 3, but I do not need you to ever do it the long way, right? You can if you want to, and it will always work this longer way, but it's just silly to do something a longer way when there's a much shorter, quicker, more efficient way to get to the answer. Okay, so let's read the long way. What you have to do is find the highest powered term, right? The term with the largest exponent overall. And then we're going to divide the entire fraction by that one specific term. The goal when we're doing this is to only have constants, just numbers left over, and also terms with x's in the denominator. Okay, so let's use that strategy on this first example. Let's see, can I zoom it in anymore? Yep, okay, a little bit. So here I have the limit as x is going towards infinity, so we're trying to see what does this function do on the right side of the graph. So I'm looking at it. Again, I'm going to do this one the long way, and then we can come back and check it with the other 2 methods as well. But what I'm going to do is I'm going to find the biggest term overall, which here the biggest term is x squared. So we're going to take this and we're going to divide everything by x squared. All right? So we're still going to be having the limit as x is approaching infinity, but we're going to take all 4 terms and we're going to divide them all by x squared, right? This is the longer way of doing it. Let's go for it. X squared divided by x squared would be 1. Now we have negative 1 divided by x squared, so I'm just going to have 1 over x squared. 5x squared divided by x squared would be 5, and then you have your plus 1, so that's going to end up being plus 1 over x squared, right? So we divided everything by the biggest term. That way we had constants left over. We like numbers, but then the only terms that had the x's in them ended up having the x's in the denominator, which was important, right? Because now we're going to evaluate it. We're going to change all of these x's and we're going to plug them in to infinity. So here we go. We got the limit. Actually, we don't need the limit notation anymore because we're about to plug it in. So we got 1 minus 1 over infinity squared is infinity. Then we're going to have 5 plus 1 over infinity. It was important that I had the x's in the bottom because then when I evaluated it, you ended up having the infinities in the bottom. And we know from that last page that we just went through that if I have a denominator that gets really, really, really big, that specific term is going to get really, really, really small. And then it's going to cancel and go away, right? That specific term goes to 0, which is why we needed to have the x's in the bottom, right? Which is why we divide by the biggest term. If you divide by the biggest term, well, the terms that started with that largest amount of x all the x's cancel, leaving you just the numbers, and then all the other original terms that had fewer than 2 x's, when I divide by x squared, right, the largest term, all of the other things that still have x's, they only have x's in the bottom, right? So you divide by the biggest amount of x, and then the terms that had that biggest amount, all the x's cancel, and you have numbers, then everything else should cancel and it should reduce, and then you're going to end up with x's in the bottom. Those x's in the bottom end up as infinities in the bottom, and then those infinities in the bottom end up being zeros, right? So if the denominator gets big, that piece gets small. If the denominator gets big, that piece gets small. And you can end up getting the answer pretty nice. If you would have evaluated it right away, you would have gotten infinity over infinity, which is indeterminate, right? But that answer is not 1. That answer needs to end up being 1/5 for this example. So just be careful. Okay, I'm going to go ahead and do it kind of the second way to kind of show you the shorter way that I would like for you to do it. And then for probably the next couple of examples, I'm going to only do it the shorter way. Right, so the shorter way is to find the single largest term on the top, and then also the single largest term on the bottom, and then we're only going to work with those 2 terms, and we're just going to straight up ignore everything else, right? So here I'm still going to have the limit as x is going towards infinity, but I'm going to look at what this question starts as, and I'm going to kind of find, like, hey, in the numerator, what's the bigger term, the x squared or the 1? Well, clearly it's the x squared. So I'm going to just focus only on the single largest term in the top, and then also I'm going to look in the denominator, and I'm going to find the single largest term in the denominator, and then I'm just going to ignore everything else. Like, even if this numerator had 17 terms, you would find the one biggest term, you would ignore the other 16. And if the denominator had 20 million terms, you would find the one biggest and you would ignore the rest, right? You only need the one biggest term on the top, the one biggest term on the bottom, and then you can go ahead and reduce some x's here, right? You got an x squared on the top, you got an x squared on the bottom, so those will all cancel. Then you have the limit as x goes toward infinity, but all the x's ended up canceling. So since there's no more x's, you don't have to change anything to infinity. So then that one you should end up getting 1/5 for the answer, right? Whether you do it the longer way or whether you do it this shorter way, you should be able to get the same answer. And then really this fastest way, which I would want you to do really just to check your answers, if you think about your horizontal asymptotes, going back to this original function, right? Because what we're trying to do is figure out what's the right-sided in behavior of this rational function. Well, the degree on the top is 2. The degree on the bottom is 2, so the degrees are the same. And if the degrees are the same, what you would need to look at is the ratio of the coefficients. So since that horizontal asymptote is 1/5, we know, right? Remember, going back to this, we have that horizontal asymptote that was 2, and then both the right and the left ended up going to that same value, because as the graph goes to the right and as the graph goes to the left, it always is going to approach your horizontal asymptote. If you can remember your horizontal asymptote rules, something like this is a 2-second question. You just think, hey, what are the degrees? Know your horizontal asymptote rules, so the asymptote's 1/5. Therefore, I know this answer of your function is going to just end up being 1/5. If you can find what the horizontal asymptote is, then that will give you the right answer. Now, you have to remember, that is only going to work for a rational function. So if you have something like on example 6 or on example 7, which we'll see later, it's not gonna work, right? But you have the 3 ways to do it. The longer way, where you divide everything by the biggest power, that gets x's on the bottom, and those terms end up canceling, and then you just have the constants left over. That's great, but you don't have to do it that way. It'll work, but it's just longer. The middle way is kind of what I hope and would encourage you to do. You find the one biggest term on the top, you could ignore everything else. You find the one biggest term on the bottom, you could ignore everything else, and then you just reduce it, and then you can evaluate it. And then you should check your answers by using your horizontal asymptote rules. Okay, let's fly through the next 4 really quickly. And I'm only going to do that kind of middle way, the shorter way here, right? Where I'm going to find the big term on the top, the big term on the bottom, and then we'll just ignore everything else, right? These are going to be pretty quick. All right, here we go. This example, limit as x goes towards infinity, we have 3x plus 5. The 3x is the bigger term, so I'm going to ignore the plus 5. Then I have a 2x squared minus 7x, So I'm going to ignore the smaller term. Right? I'm just going to find only the biggest term on the top and then only the biggest term on the bottom. So this is what I'm going to work with. Reduce it. So you're going to have a 3 over a 2x. Once I reduce it, then I go ahead and I can evaluate it. So I'm going to have 3 over 2 times infinity, which is 3 over infinity. Right? 2 times infinity is infinity. And I know if the denominator gets big, the fraction overall is going to get really small. So that one's not too bad, right? It's just pretty quick. You find the biggest term in the top, ignore everything else. Find the biggest term in the bottom, ignore everything else. Then you can reduce it, and then you can evaluate it. You can check by using your horizontal asymptote rules. The degree on the top was 1. The degree on the top, on the bottom was 2. Since the denominator is bigger, the asymptote would be the x-axis, y equals 0. So if you know that horizontal asymptote rule, really you could get this answer very, very, very quickly. But I would like for you to show this amount of work. Okay, example 3. Now we're looking at the left side of the graph. That doesn't matter, right? These same strategies are going to work either as you go towards positive infinity or negative infinity. It's fine. So here I'm going to find the biggest term on the top, ignore everything else. Find the biggest term on the bottom, ignore everything else. And then let's reduce it. I still have the limit as x is going towards negative infinity. Let's see, it looks like 1x is going to end up canceling, but I still have x over 4. And then I can go ahead and I can evaluate it. Plug in the negative infinity for your x. Then I have negative infinity divided by 4, which gives you the answer of negative infinity. Now, if you think about your horizontal asymptote rules, the degree on the top was 2, the degree on the bottom was 1. So here there wasn't a horizontal asymptote, right? There was no horizontal line that bounds the growth of the graph, right? That tells you what number the right side and the left side are going to approach. So if there's no horizontal asymptote, you know the right and the left side, they're either going to go up forever and ever and ever on the right side, or maybe it could go down forever and ever and ever on the right side. And then same on the left. Like maybe the left side goes up, or maybe the left side goes down. You don't really know for sure, right? If I know the degree in the top is bigger, you know the answer is either going to be a positive infinity or a negative infinity, but there's no way to know whether the plus or the minus is there without actually doing a little bit of work, right? So the horizontal asymptote rules are really nice and are really fast when there is a horizontal asymptote rule, but when there is no horizontal asymptote, you have to do something to figure out if you want the negative or if you don't. Okay, example 4. Limit as x is going towards infinity, 3 minus x over 4x plus 1. Again, find the biggest term on the top, ignore everything else. So I have a negative x. Don't ignore this negative, right? That negative 1 coefficient is attached to the x. So I have a negative x over 4x. You have an x right there that will reduce. So negative 1 over 4. And then the limit of a constant is that same thing. Okay, and again, you could check this by using your asymptote rules. The degree on the top's 1, the degree on the bottom's 1. So then you would just look at your coefficients. You have a negative 1 over 4, right? This limit stuff is why the horizontal asymptote rules are the way that they are, right? This longer way of doing them is why we can use the shortcut rules for the horizontal asymptotes, right? Those don't just come out of nothing, right? There's calculus going on behind the scenes for those horizontal asymptote rules. But if you remember them, then you can just use the horizontal asymptote rules. Just have to be careful. If there is no horizontal asymptote, you need to do something to figure out what the answer is, either the positive or the negative infinity. Okay, let's do example 5. Limit as x is going towards negative infinity, 5 minus x squared over 4x plus 1. Find the biggest term on the top, ignore everything else. Find the biggest term on the bottom, ignore everything else. Looks like you're going to have 1x. That's going to reduce. See kind of how lazy I'm being? I'm not even writing out a whole lot of work. I'm just canceling and reducing stuff. That's perfectly fine. But probably at least want to show something. Like once you got it all reduced, I see I'm going to have a negative x over a 4. Right? So if you want to do all your canceling and you're ignoring in the same step and then just rewrite and regroup everything that you have left over, that's okay. And then here I need to evaluate it. So I need to change the x to negative infinity. Remember, I had negative x. So I have negative, and then I plug in the x value was negative infinity. So then those two negatives are going to end up canceling. You had a negative that was already in the question, and then you change the x, you plug in another negative from the negative infinity. So then this answer is going to end up being a positive infinity. Okay, let's see. Next one. Here you have a subtraction. If you were to plug it in, you would get infinity minus infinity, which please do not tell me that's 0. No, 5 minus 5 is 0. That's a property of numbers. You know 5 is the exact same thing as 5, so they're going to cancel. But infinity is kind of a weird abstract concept, right? Infinity plus 1 is the same thing as infinity, right? They're both infinitely, unimaginably huge. So you don't necessarily know that this term being described as infinity and this term being described as infinity, you don't know that those two things are the exact same size. So you don't know that they're going to cancel and give you 0. It could, but you don't know for sure. It's basically the same reasoning why infinity divided by infinity is not 1. That's a property of numbers, and this infinity is more of an abstract concept. It's not an actual physical number that you can work with. All right? So here it's a little bit stranger. You can't just plug it in and you can't evaluate it, but what we're actually going to do is that, so here I just want to write that note for you. Infinity divided by infinity also is not 1, right? So please don't ever do that stuff. If you hit infinity minus infinity, or if you hit an infinity divided by infinity, you have to do something. And what we're going to do for this question is a little bit sneaky. We're actually going to turn this subtraction question, and we're going to turn it into a multiplication question. So here, check it out. I'm going to factor out an x. And then now, instead of a subtraction problem, now I've got a multiplication, right? I've got x times this chunk. And now if I plug it in, now I'm going to have infinity times infinity. And that's fine, right? Infinity times infinity is infinity. You don't have any problems when you make stuff bigger. Infinity times infinity is infinity. Or infinity plus infinity is infinity. Or infinity to the infinity power is infinity. If you're starting with stuff that's abstract and you're just trying to make it bigger, well, it's going to stay abstract and it's going to stay infinitely huge. The problem comes when you try to go from the realm of abstract stuff that's infinitely huge and you try to reduce it into something that's very small and very concrete, right? So no, those can't be done. Yes, those can be done, right? You don't have a problem making infinity bigger. It's when you try to make it smaller. Okay, I'm actually going to pause this video for now. Those of you who are in Calculus AB, you don't need to worry about this next example. When I start the next video, I'm going to do it, so you can follow through if you want, but really this next example is something that comes up more for the Calculus BC kids. So just know that at the beginning of the next video, you guys can go ahead and kind of just skip it and go to the stuff at the next page, but Calculus BC kids, you guys would want to watch and want to pay attention to me doing this.